Alright, in the last video we computed the curvature for a few different paths using this second expression for curvature that you see here. Okay, this is the magnitude of the derivative of the unit tangent vector with respect to time divided by the magnitude of the velocity vector. But as it turns out, this expression can be a mess computationally, at least for certain vector functions, and so in this video we're going to derive some alternative formulas for curvature that will make things easier in some instances. Okay, so I have a path here, and if we're located at this point, I've drawn our velocity vector here in green, and our acceleration vector, which is just v prime, in red, and our unit tangent vector, t, is by definition the unit vector that points in the direction of our velocity vector, and it's equal to the velocity vector divided by its magnitude. Or put another way, the velocity vector is the magnitude of the velocity vector times the unit tangent vector. Okay, now if I go ahead and differentiate the velocity vector with respect to time, that, as we noted over here, gives us the acceleration vector on the one hand, but if I differentiate this expression for the velocity up above with respect to time, using the product rule, I get the following expression then in turn for the acceleration vector. Okay, this is the derivative of the first factor, so that's the derivative of the magnitude of the velocity with respect to time, times the second factor, which is the unit tangent vector, plus the first factor, which is the magnitude of the velocity, times the derivative of the second factor. So that's the derivative of the unit tangent vector with respect to time. All right, so now what I'm going to do, I'm going to take the velocity and acceleration vectors and form their cross product. Okay, and for the acceleration vector, well, I'm just going to replace it with this expression we just derived up above in orange. Okay, now let's go ahead and take this velocity vector and distribute it, because we know the cross product is distributive. And also note that the derivative of the magnitude of the velocity vector with respect to time is a scalar function, right? Because the magnitude of the velocity, in other words the speed, is a scalar function. And likewise right here we have a magnitude of velocity. Well, that's a scalar. So when we go ahead and distribute the velocity vector in, okay, then we're going to get this derivative out front, and then I get a v cross the unit tangent vector, and then I have the magnitude of velocity in front as well here, and then I have a v cross this derivative of the unit tangent vector with respect to t. Okay, great. So now note that since the velocity and the unit tangent vector are parallel, this cross product, v cross t, is actually 0. And so this entire expression simplifies to just the second term, which is the magnitude of the velocity times this cross product of v and this derivative. Okay, now I'm going to take the magnitude of the cross product of v and a. And so from this expression, that's just going to give me the magnitude of the velocity vector times the magnitude of this cross product. Okay, and now I'm going to use our key result on the magnitude of the cross product that says the magnitude of a cross product is the product of the magnitudes of the two vectors you're crossing times the sine of the angle between these two vectors. Okay, so I've taken this magnitude of the cross product and I've broken it up using that result on cross products. Alright, and now off to the side I want to note that since the curvature kappa is equal to this ratio here, right, where I have the magnitude of the derivative of the unit tangent vector with respect to time divided by the magnitude of the velocity vector, okay, multiplying both sides by the magnitude of the velocity gives us that the magnitude of this derivative is equal to the curvature times the magnitude of the velocity. So I'm going to replace the magnitude of the derivative of the unit tangent vector with this expression, right, which is the curvature times the magnitude of velocity. And notice here I have 1, 2, and now 3 factors of the magnitude of the velocity vector. So I really get magnitude of v cubed, and then I have my factor of kappa here I put out in front, and then I still have my sine theta. Okay, so now I claim that the angle between the velocity vector and this derivative of the unit tangent vector is 90 degrees. In other words, I claim that these two vectors are in fact orthogonal, which will imply, since theta is 90 degrees, that this sine theta term will equal 1. But let's go ahead and show that here off to the side. So the claim is that the velocity vector v, which up in our diagram is this vector in green, is actually orthogonal to the derivative of the unit tangent vector with respect to time, which I've indicated here in purple. All right, so how do we prove this? Well, we're just going to use the fact that the unit tangent vector has magnitude 1 for all t, right? So that implies that if I take t dot itself, which is the magnitude of t squared, that's also equal to 1, because I'm just squaring 1 there. And now if I differentiate both sides of this equation, I'm going to use the product rule for dot products on the left-hand side. Okay, so that gives me what you see on the left. And then on the right, I'm just differentiating a constant. I'm differentiating 1, so that gives me 0. And now I can use the fact that the dot product is commutative, so I get 2 times this dot product is equal to 0. And I divide both sides by 2, and you get that the unit tangent vector t dotted with this derivative is equal to 0. Okay, so if I just pause right there for a moment, that says that the blue unit tangent vector is in fact orthogonal to this purple derivative vector. But see, the unit tangent vector in blue is parallel to the green velocity vector, so in turn v is perpendicular to this derivative vector. They have a 0 dot product. Okay, so that implies, as we just noted, the angle between our green velocity vector and this purple derivative vector is 90 degrees. They're orthogonal, and so the sine of theta is in fact 1. So this simplifies to just kappa times the magnitude of v cubed. Okay, so now what I'm ultimately after here is an expression for the curvature kappa. So if I divide both sides of this equation now by the magnitude of v cubed, that's going to give me the following formula for curvature. And I'll refer to this as an alternative formula for curvature, as does our textbook. And this is kappa equals the magnitude of the cross product of the velocity and the acceleration divided by the magnitude of the velocity cubed. All right, great. So now what I want to look at is the scenario where we're working with a curve in the xy plane that's described by an equation of the form y equals f of x. Okay, so here, if I take any point on our curve and label its coordinates x comma f of x, then I can form this position vector that I'm going to call r of x, and in components that's just x comma f of x, right? So here I'm going to take as the parameter for the curve just the x coordinate on the various points on our curve. Okay, so here you want to just think about x as equivalent to the parameter t. Alright, so now let's go ahead and derive our velocity and our acceleration vectors, because I'm going to go ahead and apply this formula we just derived up here for curvature to find an expression for the curvature in this instance when we're working with a plane curve given by this kind of an equation, y equals f of x. So here are our derivatives, right? So just differentiate the position vector component-wise to get the velocity vector, so that's 1 comma f prime of x. And then to get the acceleration vector, just differentiate the velocity vector component-wise, so 0 comma f double prime. And now I'm going to find the cross product of the velocity and the acceleration. So for the velocity, well, the I component's 1, the j component's f prime of x, and the k component is 0. And then likewise the acceleration vector, well, I component 0, j component's f double prime of x, and the k component is 0. Now to compute this determinant, you just expand as usual, and you wind up getting 0, 0, and then f double prime of x. All right, so the curvature, according to this formula that we derived here just a bit ago, right, that's going to be the magnitude of the cross product of v and a. So taking the magnitude of this vector, well, I'm going to get the square root of the sum of the squares of these components. So I'm really just going to get the square root of the square of f double prime of x. Now be a little careful there. That's not going to give me f double prime of x necessarily, right? Because I'm taking the square root of the second derivative squared. Right? I have to take into account that f double prime could take on a negative value. So here I need an absolute value for this magnitude. Now downstairs I have the magnitude of v cubed. Now up here I just noted that the magnitude of v, well, that's just the root of the sum of the squares of the components of v, so that's the square root of 1 plus f prime of x squared. So down here I want that cubed, and if you cube a square root, that's equivalent to just putting this expression to the 3/2. Alright, great. So now what I want to do is just summarize everything that we've seen up to this point on curvature. Okay, so for curves in R2 or R3 that are described by a vector function r of t, okay, well, we have for our definition, curvature is the magnitude of the derivative of the unit tangent vector with respect to arc length. Okay, now using the chain rule, we were able to derive this first formula that we applied in the last video. This is the magnitude of the derivative of the unit tangent vector with respect to time divided by the magnitude of the velocity. Okay, and as we've noted in this video, sometimes this can be a computational mess, so we in turn derive this formula, which is the magnitude of v cross a over the magnitude of v cubed. Okay, and then lastly, in the instance when you're working with a curve in R2 described by the equation y equals f of x, we have this formula that can tell us the curvature. Alright, great. Well, that's a good place to stop. We're going to apply all this stuff in the next couple videos. Thanks so much.